Hello world, here's Jorge, and let's continue learning about object detection in PyTorch. So last video what we did was to upload the data from the GitHub repository of VGG, and now what we want to do is to explore such data. So what we want to do now is to first we're going to visualize some random images in order to have a flavor, so get a flavor of what kind of data we're dealing with, what kind of images. And next, we're going to understand deeper the data structure that we're going to be dealing with in this practical. Okay, so let's get started. We're going to now visualize our data. Okay, let's mark that down. And so now let's just get started by saying, okay, we're going to visualize some random images. Okay. Okay, so to get there, to get to the point where we essentially, well, let's add another character here so that it's a bit smaller. Okay, so now we want to actually explore a little bit before we go straight to the random images analysis. Let's explore a bit more our folder, okay, because we want to find out how many images we have in the actual main folder, and also how many images our subfolders contain. Okay, so to do that, what we can do is to define a path, define a mother path, and from that mother path just basically screen, so basically scan our main data folder to find out more information, more quantitative information about the data that our main folder contains. Okay, so let's do that. So first we need to define a path. Okay, so let's do that. So from pathlib, we're going to import the function path. Okay, this is going to allow us to define the, say, main path. Okay, so this main path we can call it, for instance, image. Let's say image path. Say, and now what we are going to do is say, okay, so we want to define a mother path, and we're going to state, okay, it's going to be content, and what else? Well, we are in content and we want data. So remember, all the key information is stored in the mother folder called data. So we need to edit a data. All right. So let's do that. So data here. Fantastic. So now we already have this mother. Well, actually, let's have a look at it. Right. So image path. Great. So here we have it. Yeah. Fantastic. So let's continue. Now we want to actually scan this mother folder, and we can do that by defining a function. Okay, a function that explores for us this main directory. Okay, so let's call that, for instance, I don't know, explore main directory. Yeah, so explore main dir, and here we're gonna say, okay, we're gonna take this image path. Okay, but as a function, let's just write a dummy name here. Okay, now how do we proceed? So what's useful is to state a docstring so that it's more clear what this function is doing. So basically it's going to walk us through the target directory, basically returning basically the contents. Yeah, it's contents. Okay, so how do we start? So we want to actually look through. We're going to look through these essentially our main image folder, so the mother folder. And what kind of information are we going to need here? So we're going to need the number of folders. Okay, we're going to need the number of images that that folder contains. And also we want to explicitly print out the path of that, say, folder, or in this case subfolder, that we're analyzing. Okay, so for that, well, let's include those variables that are going to allow us to do that. So path there for the, essentially with the path, for the path to show up, and then names there for the names of the directories and names of the files. And okay, and to look through the actual folder, we need to call out. OS, okay, because Python has for us a function called walk. So os.walk, and here we're going to include, okay, what is the folder that you want to, say, screen, that you want to scan. So that's going to be, of course, the, well, in this case, the dummy. This, we call it path. We just call it path there, I think. Yeah, right. Now the doc string is hiding this. Okay, path there. And we have that. And we're going to print this out. So we're going to need to print the information. So it's going to be the following. Oops. So print. And we're going to have, there are. So there are X directories. So the name of the directory. So for that, we included these names there. There are X directories, and what else? And what else? Well, we need the number of images in the specified path. So, and the name of the files, but we need the length of that. Okay, so it's going to be the length of the names files. Okay, so X images in these path there, yeah. So, well, in this case, this path there, yeah. But remember, in this case is the path there that it's basically on index in the loop, right? So path there. We have the underscore, okay. Well, and it's a path, so let's put here. So. Yeah, okay. Okay, so let's call it out. Let's call this function. So explore main there, and we are gonna say, okay, is the image path that we want to do. So this should, if it works, should give us the actual information that, oh, what is going on, because this should print out the actual say string that we wrote within. So there's something missing here. Let's think about that. Probably the mistake has to be in how we define the image path. Okay, has to be there. So let's have a look. Okay, I think I might have what happened. So essentially, sometimes if we don't put a slash in front of the say main folder, it could yield basically to, or could lead to an error, because when we specify a slash in front, we are making our comment independent of the, say, current working directory. Okay, so in order to make our path independent of the current directory, because we are sure that this path is correct, because we can just see it, it's obvious, right? So with specifying here a slash, now it's independent of the current directory. So given that the path is correct, it should work. So let's see. Fantastic. Okay, so now you can see that we have 4 images in the science directory, okay, which is it's here, okay. Well, there are 4 images, sorry, in this path, okay, in the contents data, which is contents data, so these images, okay, and then within this path, okay, which is the science, okay, we have 600 images, which makes sense because all these JPEGs are here, and no directories. Okay, fantastic. That's good to know. That's good to know. Okay, so what else? What else can we do? So essentially, now what we can do is just to proceed, and print out these images, okay, the random images that we said we were going to do. So we're going to leverage the, say, power of randomness here. So we're going to import random, okay, let's import random, and we are going to essentially we're going to plot the images using a PIL library in Python. Okay, there are other options specific actually to PyTorch. I think there's something called io.read in PyTorch, if I'm not mistaken, something like that. Yeah, read image, exactly, like pytorch.io.read_image. This is also going to work. Okay, this is another method, but let's focus now on PIL. Fantastic. So for that we need to first import. So from PIL import image. Okay, fantastic. So now let's first actually get all the paths, because what we're going to do now is to get all the image paths, and we're going to use those image paths to actually select one randomly from that list, and that is the one that's going to be plotted out. Okay, so we're going to get first all image paths, and we're going to store that information in a list. So we have image path, and it's going to be a list. So fantastic. So now we're going to make this a list, and we're going to say, okay, what is the mother path? So it's going to be image path, and okay, so how can we collect essentially all the image paths within the mother path? There's something called in Python, there's a function called glob that is actually allow us to do this. So glob, and now let's have a look again at the structure. Okay, so if we go to data, because now remember our mother path is content data. Okay, so is this, but now what we want to do is to basically scan through all these main folder to get all the image paths. So to do that, we need to understand how many sublevels do we have. So we can see, let's just have a look here. So we see one here, this is one sublevel, but there's just one folder. So let's get into the second level, and there's just a second level. So this means that we need to specify, okay, all the files within the first level, then all the files within the second level, and dot the extension. And watch out, because we need to make it right here. If we say write down JPG with an E, it's not going to work. Okay, so watch out there. So it's going to be JPEG. And what is this printing? Oh, because this needs to be a string. Of course, this is a string. Okay, fantastic. Yeah. So now, what else? Second step, which is going to be picking a random image. So select a random image from this list of image paths. Okay. So we're going to call this, so it's just a simple random image. Okay. So, and it's actually going to be a path. So it's going to be the path corresponding to this random image. And okay, how do we do that in Python? So random dot and choice. Okay. And you specify the list of image paths. So there we go. There we go. Fantastic. So now we already have this random image. How can we continue? So now let's actually plot it out. So for that, first we need to use the image function. So to do that, so yeah, let's first specify 3, open the random image. Okay, open the random image. And let's call this just img, and we can do the following. So it is image.open, and here we need to specify the random image path. Fantastic. So now let's just, for the sake of getting more information, now let's just print out as well the height and the width of the image. Okay, so let's print this collection of metadata. So we're gonna have print, I'm gonna have here a random image path, and we're gonna have this see here, random image path, so that we explicitly get the path of the image that was randomly selected. And now let's print out the height. And how do we do that? So there's a command in Python that allows us to do that. So it's going to be basically, okay, the image that we are going to open using a PIL dot height. Okay, and let's do the same with, okay, let's do the same with the width. So image width, and analogously we get the image width. So okay, so remember, we need to call out the variable image, otherwise it will not print out the image. Okay, so now let's see. Fantastic. Okay, here's the random image. Oops, but I didn't see any road sign, but okay. But anyways, here we have it. Okay. Here we have is actually clear. And now to get, just for fun, a couple of more random images. Okay, now at least it's visible. You see, it's a clear, say, mandatory sign here. And just one more for fun. Great, so here we have it. Okay, fantastic. We get a feeling of what kind of images. So yeah, of course they are road images, and the goal is going to be detect these road signs. Okay, fantastic. So let's continue now. Let's continue with our analysis. And now what we want to do, because we already got a feeling of these kind of images, because we randomly say visualize some of them, and now what we want to do is to understand the structure of our data set. What do I mean by that? So essentially, let's have a look. We have the data. Okay, we have the data. We have visualized some of the, well, of course, random images from the science folder. But if you have a look here, we have a folder. We have a file called sciencedata.pth. Okay, what is that? So that folder actually contains a lot of information about the data set, and it's going to be actually structured in a way that is going to be, say, very helpful to explore. But let's have a look at this extension, this PTH. This indicates that right now the file is not in, say, a human readable format. We cannot understand it as it is right now. So because essentially it's serialized, okay, it's pickled. That meaning that we have this file with just binary numbers there. So what we need to do is to actually load it in a way that we can understand it. Yeah. So actually there's a class in PyTorch that does that for us, and it's called torch dot. So it's dot load. Okay. Torch dot load. And as you can see, what it's going to do is to unpickle, to deserialize this folder for us, so that we can actually get a look, get a better look at its contents. Okay, so let's do that. Let's just have a look at it. So let's call this data, for example, and this I'm going to say is going to be equal to torch dot load. And here we need to specify the string. So we need to specify the path where this file is located at. So it is in data and the name of this file. So it's going to be data, there's a string, data, and signs data.pth. Okay, fantastic. So that's great. Oh, you see this torch has curly underline on it. So this means that we have a not imported torch. So import torch. Fantastic. So now what we are doing now is loading this file. Okay, in a way that we are going to be able to understand. It's going to depickle it for us. So let's see if it works. Yeah, great. It looks like it did. So now let's have a look at it just randomly. Oh wow, that's a lot of information there. Okay, but now what I'm worried about is to actually get to find out what kind of object this, so what kind of structure this is. So yeah, it looks like it's a dictionary. Okay, this is a dictionary data structure. So okay, and as you can see, we have apparently, okay, we have the key here, but as values of this key we have another dictionary. So this looks like we're gonna have like top level keys and some sub keys within. Okay, but to verify that, just let's code it out. So data dot and these keys I want to find. So we want to find out what are the top level keys in this dictionary. Okay, so great. So it looks like it's train and val. So we have two top level keys in here. Okay, now let's ask ourselves the question, okay, so what are these subkeys? So what are the corresponding subkeys for these top level keys train and val? Yeah. So to do that in Python, what we need to do is, okay, say data, and we need to call the top level key of interest. Say for instance, let's start with train. And once we have done that, we actually get the keys associated to that specific top level key train. Yeah, let's have a look. Great. So it looks like we have images, boxes, box images, box labels, and box patches as subkeys of the main or top level key train. Okay, so let's think about that, because what we can do now is to actually get the subkeys of the val top level key. Okay, so to do that, we just simply copy paste this and key, and here we're gonna say, okay, now I want the val subkeys. Okay, fantastic. So they are the same. So they have the same subkeys, both train and val. This is really good to find out. So what can we do next? So what we can do now is actually get to explore, because we already found out that the subkeys, that there are five subkeys corresponding to train and val each. Okay, so now let's actually explore what values do these subkeys say have associated to. So what kind of values do they have associated to? So to do that, we are going to go one by one, just exploring it. Okay, so let's start with the images, and I'm going to focus on train. Okay, I'm going to focus on train because actually for the value they are going to be essentially the same. Okay, so let's focus on train and do all for train. So train, and now let's start exploring the images. Great. So let's just let's print all them out. Yeah, let's print them all out. Okay, so that's a lot. Yeah, so just to get started, I just want the five first elements. Okay, the first 5 values associated to say the subkey images. Okay, here we have it. Okay, fantastic. So it looks like they are paths. Okay, so these images, so the subkey images looks like they store image paths. Okay, it looks like that. But let's continue. Now let's do the same for boxes. So let's just copy paste this, and we're going to say, instead of images, we're going to say boxes. Fantastic. So it looks like we have a 4D vector per box. It looks to me like that, and they are tensors. Great. Well, let's just verify that there's one per box. Yeah, exactly. So we have the actually we have one 4D vector per box. Okay, it looks like these are specific coordinates to the box. We'll find out more about them. For now, it's good to just know that there's a 4D vector associated to each box. Okay, great. So next, what do we have? We have box images. Okay, so let's do that. Box images. Images here. Okay, so they look very similar in format to what train images are, right? So the natural question here is, what's the difference, right? So what is the difference between images and box images subkeys? So to just get a better understanding, let's just print out more so that we can just have a naive comparison, right? Okay, so it looks to me that these paths are unique. That's my guess, because you can see there's no repetition whatsoever in this list. But here, yeah, here we have some repetitions. Okay, and as we'll discover later, actually what's happening is the following: that per image, okay, we can have multiple bounding boxes. So if in an image up here there are, say, 3 bounding boxes, then we're gonna have, say that image is 1, then we're gonna have these paths repeated 3 times, because there are 3 bounding boxes in that specific image. That is the main difference between, say, box images and images, where images are actually just the plain image of paths for all our data. Okay, so that's why they are unique, because there's one for each image. Okay, great. So let's continue now with the next subkey, which is going to be box labels. So let's do that. Box labels. Great. So exactly, they are just class labels. So per box, we're gonna have, say, a label to it. we're gonna label each box with a number, and that is what this number is representing. Okay, and what else? What else do we have to actually analyze? So what's next is these box patches. These box patches. So just have a look at that. Box patches. Let's have a look. Oops! Wow, that's a lot of information here. Yeah, a lot of information. I just want to know about one. Just give me the first. Okay, so this looks to me like a 3D vector. Yeah, how do I know that? Because there are three say brackets here. That's a trick to know that. So what? Okay, so let me print actually the shape of this. So print the shape. Okay, great. So it looks like, yeah, we have a 3D vector with actually 64. This looks to me like the size of the image. Okay, so this actually, yeah, is actually a cropped image of the of a given image, of a given general image. This is my guess. Okay, and these three looks to me like these so these red, green, and blue color channels. So there are three color channels. Okay, but yeah, we'll find out more about these box patches next. But yeah, at least we have a really good understanding, or have a say hands-on understanding of what kind of information, what kind of values do we have associated to the subkeys of our dictionary. Okay, so now what is going to be actually useful is to know, okay, how many boxes do we have? Okay, how many boxes do we have? And to actually get to know that, what we can do is to have a look at these boxes, right? So each box is going to have one 4D vector associated to it. Okay, so what we can do is to get the length of this. Okay, so if I get the length of the train boxes, I'm gonna get the total number of boxes for training. Okay, so let's do that. Let's print that out. So this is going to be the number of boxes. So number of training and validation boxes. Okay. Great. So let's do that. So let's print. Yeah, let's do this. So number of training boxes, and what I can do is, okay, so the length of this, the length of this. Okay, let's see if this works out. Great, exactly. So there are 691 boxes in the train for training. Okay, so let's find out how many boxes do we have in the validation set. Okay, validation here. Okay, great. So we have actually just say, yeah, it looks to me like this above, yeah, around 75% or so. Training boxes and the rest for validation. But let's actually code it out, right? So let's code out the actual percentage of this. So what is the percentage of training boxes? So very simple. Let's just actually get we're gonna need the sum of these lengths. So I'm actually curious if we can do that with the sum function in a Python, like directly. Can we actually add like that? Just add length like that? Let's see. Let's find out. There's no better way than just try it out. So let's see. Oops, no, doesn't work. Int object is not iterable. Iterable, okay. Let's think about this. So, okay, an integer is not iterable, okay, but what's iterable is a list, right? So if we convert this, because now these are integers, but if we convert this into a list, is it going to work or not? Huh. Let's get this here like that. Okay, let's find it out. Oh, great, it worked. So it's about 80% actually, more than, yeah, okay, 81%. So 81% of boxes are going to be training boxes, and this 90% is going to be validation boxes. Okay, but yeah, that's actually what I had in mind for this video. And what are we going to do next? So what we're going to do is actually load the data and filter it. Okay, well, we already loaded it with the stores.load that we did above, right here. Yeah, right here. We loaded and deserialized this science data path file, PTH file. But now what we're going to do is actually to filter it, okay, in the next. So thank you very much for your attention, and I am willing to see you very soon.